This is AP Calculus, Notes 3.1, video 2 of 4. We are going to use the product rule given a function in equation form. So the directions, use the product rule. We're going to mix my notations here so we can see how this looks with different notations. Lagrange notation is prime notation, f prime. Product rule, I'll take the derivative of the first function. That's going to be 4x plus 3. It's more than one term, so I got to put it in parentheses, times the second function plus the first function times the derivative of the second function. The derivative of x squared minus 3 is 2x. It's only one term. I don't have to put it in parentheses. If it makes you more comfortable to put it in parentheses, go for it. As far as the derivative is concerned, this is finished. But a lot of times on multiple choice, if you're given a question like this, it's going to be in polynomial form, meaning there's not going to be all these parentheses. So if we do some algebra to this, if we multiply the 4x times the x squared, we're going to get 4x cubed. 4x times minus 3 is a minus 12x. 3 times x squared is a 3x squared. 3 times a minus 3 is a minus 9. If we distribute this 2x, we're going to get 4x cubed plus 6x squared. Combine like terms, we got some cubes up in here. We got some squareds. So f prime of x is going to be 8x cubed plus 9x squared minus 12x minus 9. Let's check out number 2. We will use Newton's notation for this little fella. First function, sometimes it helps to do this. First function, second function. So Newton notation, s dot. Take the derivative of the first function, it's the power rule, times the second function, plus the first function times the derivative of the second function. That's the derivative of the trig function sine. Now we could leave it like this, but a lot of times if we're trying to do some special stuff here, we're going to factor if we can. And this first term and the second term both have a GCF, common factor, of t squared. So s dot, we could factor that out to the front and leave it as 3 sine of t plus t cosine of t. If this was a free response question, you would not have to do that unless we need to do something special with this. So a lot of times, once again, I won't get into what that special thing is right now. But your answer could look like either of those. Number 3, let's use Leibniz notation. We're going to take the derivative of g with respect to theta. Now, this first term, we don't need to use the product rule on. This is just the power rule. This is theta to the first. So it would be like a 3 times x. We take the 1 times the 3, which is 3. Subtract 1 from the exponent. Theta to the 0 is going to be 1. So that's just going to be 3. Now the product rule is going to apply here. We're going to take the derivative of the first term. And I'm going to write this one out, even though I told you that we don't have to. In fact, I'm going to add a step here. Don't hate me, because I just added this. We're going to take the derivative with respect to theta of 3 theta, plus we're going to take the derivative with respect to theta of theta times sine of theta. This was not a required step, and what I'm going to do next for this is not also a required step. So using the product rule for this, we're going to take the derivative of theta with respect to theta times the second function, plus the first function times the derivative of the second function. Both of these steps we could have skipped, by the way. Sometimes showing more work makes things more obvious, and for some folks it makes it less obvious. So the first step that you'd have to show, the derivative of theta with respect to theta is 1. That's like saying the derivative of x. And this is times sine of theta plus, bring down the theta. The derivative of sine with respect to theta is cosine. As far as simplifying goes, we could multiply the 1 times the sine and get 3 plus sine of theta plus theta times cosine of theta. It's as simple as we could make this. Just want to make it clear that here we use the product rule. As we did right here. Only 2 steps that are required are these steps right here. All right, number 4. This one's not going to be an easy one. And I say that because we have this little fella. I'm going to rewrite this as x to the 1/2. So k prime of x, this is my first function, this is my second function. I'm going to take the derivative of x to the 1/2. That's going to be 1/2 x to the negative 1/2. Second function stays the same. I add to this, leave the first function alone, times the derivative of the second function, that's going to be 2x minus 3. Now, let's see. Instead of distributing this stuff, I'm going to actually factor out the GCF of this. And this is a little difficult mentally. We're going to factor this fella out right here. It's what both of these have in common. Now, obviously, they had the same base, x, so we know we can pull an x out. And then the part students have trouble with, do I pull the exponent of negative 1/2 out to the front, or do I pull the positive 1/2 out to the front? Let me give you a different example. If we had x squared plus x cubed, and you wanted to factor an x out to the front, would you factor out an x squared or an x cubed? Well, you'd factor out an x squared. So what's the rule? If you have the same base, the number that you put out to the front as an exponent is the smaller of the two numbers. So in our case, a negative 1/2 and a positive 1/2, a negative 1/2 is the smaller of the two numbers. So that goes out in front. And then, because we already got parentheses in this, I'm going to put brackets here, which means I just factored out this out of this whole thing. This term here, we're going to be left with a 1/2 times x squared minus 3x plus 2. Here, obviously we're going to be left with the 2x minus 3. But what becomes of this? If we go back to this little example up here, how do you figure out what exponent is left? Well, you take the original exponent and you subtract from it the exponent you put in front. 3 minus 2 is 1. 2 minus 2 is 0. So we have 1/2. We subtract from it a negative 1/2. 1/2 minus a negative 1/2 is like 1/2 plus 1/2. So we are left with x to the first. We don't need to write to the first here. I just did it for emphasis. Now at this point, we can distribute this half, distribute this x, and since this is being multiplied by this whole thing, we can make this a positive exponent by making this whole thing a fraction. I'm going to put this on the bottom now. It's going to be x to the 1/2 on the bottom, which means the square root of x. If I distribute up here, I get half x squared minus 3 over 2x plus 1. If I distribute here, I'm going to get plus 2x squared minus 3x. We've got some like terms. 1/2 x squared plus 2x squared. You could say that's 2.5x squared. I personally don't like having fractions and decimals, so I'm going to write it as 5 over 2x squared. Another pair of like terms. We got a minus 3 over 2x and a minus 3 over x. You could think of this as minus 1.5 and a minus 3 is a minus 4.5. Once again, I don't like decimals in my answers when they're fractions. If you want to leave it as a decimal, you can. 1 has no like term. This is over the square root of x. So this is what k prime of x could look like. I say could because if it's multiple choice, it's like the Wild West of what they're going to write for their answer. I think this is the most likely scenario, but I don't know. Number 5. Let's use Leibniz notation. The derivative of h with respect to x. Straight up product rule. Take the derivative of 3x plus 2, the first function, that's 3, times the second function, plus the first function, it's multiple terms, so you got to put it in parentheses, times the derivative of the second function. The derivative sign is negative sine of x. Best we can do is we can pull there's no GCF of these two terms. The answer could look like this. They could have also moved the negative out here. They could distribute this. We'll do that. Once again, if it's multiple choice, who knows how it's going to look. It's going to be minus 3x sine of x and then a minus 2 sine of x. One more and then we'll do an equation of a tangent line. Let's say that v of t is sine of t times cosine of t. We use a little Newton, v dot. It's the product rule. We got two functions. Take the derivative of the first function times the second plus the first function times the derivative of the second. Derivative of cosine is negative sine. This can be simplified in that we can write this as cosine squared of t minus sine squared of t. Just a quick reminder, since this just came up organically, cosine of t squared is equivalent to saying cosine squared of t. It is not the same, heavy on the not, as cosine of t squared. Same, same, not same. All right, number 7. Find the equation of the tangent line. Well, to find the equation of the tangent line, we need a point of tangency. So to find this point of tangency, we're going to take function g, and we're going to put in for t pi over 6, because it tells us, here's function g, we want to know the tangent line when t is pi over 6. So that's pi over 6 squared times cosine of pi over 6. Pi over 6, what is that? It's in quadrant 1. That's equivalent to 30 degrees. Opposite the smallest angle, I'm going to call 1. The hypotenuse is always twice the short leg, and the long leg is the short leg times the square root of 3. If you want to do a unit circle style, this would be 1/2, 1, and square root of 3 over 2. Cosine is x over r, so that's square root of 3 over 2. this is going to be pi squared over 36. When you square a fraction, you square the top when you square the bottom. Cosine of pi over 6, we just said, was square root of 3 over 2. This hot mess is pi squared times the square root of 3 over 72. That is the point of tangency. Pi over 6, pi squared, square root of 3 over 72. What about the slope of tangency? Well, we got to find the derivative of g. This is the product rule. So we got to take the derivative of the first function, that's 2t, times the second, plus the first function times the derivative of the second, the derivative of cosine of sine. We can clean this up just a little bit and make this 2t cosine of t minus t squared sine of t. We could factor the t out, but that's not going to be helpful in this case. So what's g prime of pi over 6? It's going to be 2 times pi over 6 times cosine of pi over 6 minus pi over 6 squared times sine of pi over 6. It's a mess. This here is going to be pi over 3. Cosine of pi over 6, that's x over r, that's square root of 3 over 2. Square a fraction, you square the top and you square the bottom. Sine of pi over 6, that's y over r, so that's 1/2. Now at this point, if you wanted to just stop simplifying this, on the AP Calculus test, on a free response, you could do that, and you could say this is the slope. Just make sure that you put it in parentheses when you put it into the function, function meaning the tangent line. I'm going to clean this up a little bit. Going to get common denominators by multiplying this first fraction by 1 in the form of 12 over 12. That's going to give me the slope as a single fraction, 12 pi square roots of 3 minus pi squared over 72. So this tangent line is going to be y minus the y value of our point equals the slope, and boy, is this one heck of a slope. I need to make this smaller. I've used too much space. This is times the difference of x and the x value of our point, which is pi over 6. Once again, if you wanted to write this like if it was a free response question and you wanted to put your slope as this, you can. You just got to make sure that you put it in parentheses because the slope's more than one term. This concludes video 2 of 4. This was using the product rule given functions of equations.